In this video, we're going to talk about an introduction to antiderivatives. Our objectives will be to define the antiderivative of a function, to find all antiderivatives of a function given an expression for f prime of x, to define and determine the indefinite integral of a function, and given a function to find the antiderivative satisfying an initial value. So that will be a particular solution that we're looking for there. All right, let's go ahead and say that the antiderivative, which we'll also call the integral, specifically, we're going to be talking about an indefinite integral to start off with of a function is an antiderivative of f on an interval I, provided that f prime, capital F prime of x is equal to lowercase f of x for all x and I, where capital F is the antiderivative of lowercase f. So we're looking for something that looks like this. Equal sign, capital F prime of x dx is going to be equal to f of x plus c, like that. This here is the antiderivative that we're looking for. If you would differentiate this function, you would get f prime of x, which is why I don't understand why this isn't a capital F over here. It should be. So I'm just going to write it that way. This is capital F. This is, if I differentiate this function, I get what's inside here, like that. So right. Or I could write it this way. This is typically how you see it in the book. Right. Where this f of x is the antiderivative of this function that's here. If I take the derivative with respect to x of capital F of x, I'm going to get lowercase f of x. That's how they're related. All right, let's just guess and check here. You guys have done lots and lots of differentiation, so I want you to think of something that if you differentiated it, you would get 3x squared. So what was the original function? So I think it's y equal, or f of x, let's write it this way, f of x is equal to x cubed. I'm going to go back and check. F prime of x is equal to 3x to the 3 minus 1 is 3x squared. Now, actually, our answer here is that we need to put a plus c, because actually, if I added any constant to this, then when I differentiated here, it would be a plus 0 on the end. So our antiderivative, to get all the answers that are possible, we need to add a constant of integration on the end there. That's going to be a capital C usually. What if we had the original function, or the derivative was equal to x cubed? We know it's going to have to be something that's going to be x to the fourth. So my guess is going to be x to the fourth. But I need 4 times something is going to be 1. So I'm going to say that my guess is that y is, or f of x is 1/4 x to the fourth, and plus c. Let's verify that. F prime of x is equal to 1/4 times 4, x to the 4 minus 1 plus 0. F prime of x would be 1 times x to the third plus 0. F prime of x here would be x to the third. So that's correct. My antiderivative here would be 1/4 x to the fourth plus c. My antiderivative here is going to be x cubed plus c. All right, so now that we've taken a look at some of that, let's actually look at a rule that helps us to not have to guess and check. If we have the power rule here, the integral of x to the p dx is going to be equal to x to the p plus 1 over p plus 1 plus c. We can't use the power rule when p is equal to -1 because -1 plus 1 is 0, and I'm not allowed to divide by 0. So we're going to have a different rule later that we're going to learn for when p is -1. It will have its own rule. So for any other power of x, though, positive or negative, other than -1, at fractions, roots, anything, irrational numbers, pi, all of them, as long as p is not a -1, we can go ahead and use this power rule. We're going to have our constant multiple rule. We're going to find out why constant multiples can pass through this symbol, but it has to do with limits. Once again, that since constants could pass through limits, this symbol has a hidden limit symbol inside of it. Same thing here with inheritance of limits for the sum here, that if you remember, the limit of the sum was the sum of the limits, and because integrals are going to have big limits that we're taking, that the integral of the sum is going to be the sum of the integrals, just like it was with derivatives. So let's go ahead and evaluate this, only we don't know a rule quite yet for this one. So I'm going to have to tell you that we know the function that differentiates to give us e to the x is e to the x. So that is its own rule, that the integral of e to the x dx is e to the x plus c. And we have not talked about this one. This is going to be another one where the power rule does not apply. So I'm going to have to tell you the integral of 1 over x dx, which is the same thing as dx over x, is going to be ln of the absolute value of x plus c. So that's another rule that you need to know. This is when I told you what to do when you have x to the negative first dx, when p equals -1 here. It's going to be this rule. So you're going to have your ln rule there. But we can use the power rule here, x to the -1/2 plus 1 over -1/2 plus 1 plus c. It's going to be x to the +1/2 over 1/2 plus c. It's going to be 2x to the 1/2 plus c. So this one we can use the power rule. Let's go ahead and split these up. First, we've got a monomial in the denominator, so 4x cubed over 3x squared plus 2x over 3x squared dx. This is going to be 4/3 integral of x cubed over x squared dx plus 2/3 integral x over x squared dx, 4/3 integral x dx plus 2/3 integral 1 over x dx, 4/3 x squared over 2 plus 2/3 ln of the absolute value of x plus c. 2 goes into 4 2 times. So this is 2/3 x squared plus 2/3 ln of the absolute value of x plus c. It can be really important to just memorize those basic forms and to be able to rewrite things like this. We're going to get 1 over x to the 3/2 dx, like that, because this is a square root of x to the third in the denominator. So I'm going to write this as 2/5 integral of x to the -3/2 dx. Give me 2/5 x to the -3/2 plus 1. I'm going to write as 2/2 over -3/2 plus 2/2 plus c is 2/5 x to the -1/2 over -1/2 plus c. I'm going to be multiplying by a -2 to get rid of that. So that's going to be a -4/5 x to a -1/2 plus c. I started off with a root, so I'm going to go back to a root, -4/5 root x in the denominator plus c, just so my final answer looks kind of like my original problem. So let's go ahead and make sure that you know these basic integrals here, and there's going to be a lot of them to know. So we already talked about the x to the p rule. X to the p dx is an important one that you need to know, that that's x to the p plus 1 over p plus 1 plus c. That's your most important rule to know, because most everything we're going to deal with polynomials and such is going to be individual power functions like that. We already talked about your constant multiple rule, but you need to know that the integral of cosine is sine because the derivative of sine is cosine. The derivative of cosine is negative sine, but we don't put negatives on this side of the formula, so we're going to take the negative over there. We're going to divide by it and put it over there, that when we integrate sine, we have negative cosine plus c. If I would differentiate negative cosine, I would get positive sine. The integral of secant squared is tangent. So think again how things worked with cofunctions before with derivatives, and it'll kind of help you out that these things are paired together. So I would expect the cofunction here, and I would expect it to become negative. So tangent becomes cotangent, and it's negative when it's cosecant squared. Secant tangent was the derivative of secant, so when I take the integral of cosecant cotangent, I expect a negative cosecant plus c, and I get it. We already talked about this one today, that the integral of e to the x dx is e to the x plus c. Explained why these are up here. We already talked about dx over x, or 1 over x dx, is ln of x plus c. And then these are really important for us to know in Calculus 1, so we're ready to use them when we get to Calculus 2. The arc sine is defined by, we can also write it as dx over the square root of 1 minus x squared. Whatever this variable is that's squared, the exact derivative of it is in the numerator. And we see a square root of a number here minus a variable expression there is really what we're looking for. In this one, we have no square root. We have this thing that's squared. We see the exact derivative of it up here, and that's going to be an arctangent. You also can write arcsine with the inverse sine symbol. You can write arctangent with the inverse tangent symbol, or yeah, like that. And be careful with arcsecant. It's going to have an absolute value in it. So you either have to have the absolute value over here, or you have to have it over here, one place or the other. And so we're going to have arcsecant of the absolute value of x here plus c. All right, so these three are three to be working on. You should have a good feel for 1 through 8 already. 9, 10, and 11 we talked about with derivatives already earlier on, though we didn't do a whole lot with them. It was a very short video. So go back and just practice being able to go both ways. But everything you want to be able to look at that and say, I recognize that. That's the derivative of, and you want to be able to play Jeopardy with them that way. All right, let's look at some examples here of these integrals. So we're going to split these up. So this is 1 over x dx plus sine x dx. So that's ln of absolute value of x minus cosine of x plus c. We're going to split this up as well. So this is secant x tan x dx plus 4 over x to the 6th dx. This one is just a secant x. This is a 4 integral of x to the negative 6th dx. This is secant x plus 4 x to the negative 5th over a negative 5 plus c is a secant x minus 4 fifths. And then I'm going to take that x to the 5th back down since it was a positive exponent to start off with, like that. So these are some examples of indefinite integrals where we are reversing the process of differentiation, and we can interpret an integral later as area if we're given limits of integration. That'll be the next lesson. We'll talk about the definite integral, and it has lots of applications in math and physics and engineering and all kinds of places. So really a powerful technique. We'll come back and talk about that next time. See you for the next video.